What makes embedded C optimization for small memory critical? Imagine trying to fit a large puzzle into a tiny box. That's what programming microcontrollers with limited memory feels like. Embedded systems often have very small RAM and ROM. Every byte counts because these microcontrollers might only have a few kilobytes of RAM and less than 100 kilobytes of ROM. If you waste memory, your system might crash or behave unpredictably. That's why optimizing embedded C code is so important. When memory is tight, inefficient use can cause stack overflows. This happens when functions call each other too deeply or use too much local data. Heap fragmentation can also occur if dynamic memory is used carelessly, leading to unpredictable behavior. Reducing memory use makes the system more stable and reliable. Performance and power efficiency are also tied to memory. Smaller code and data footprints mean faster access times. This results in quicker response times and less power consumption, which is vital for battery-powered devices. If your code is lean, your device can run longer on a single charge. Choosing the right data types helps a lot. For example, using 8-bit integers instead of 32-bit saves memory. Using unions allows sharing memory between variables that are not used at the same time. Static memory allocation is preferred over dynamic because it avoids heap fragmentation and reduces runtime overhead. It also makes your program more predictable. Minimizing stack usage is another key. Limit function call depth and recursion. Pass large data structures by pointers instead of copying them. Inline functions can also reduce memory needed for function calls. Writing simple, short code and removing unused parts helps keep the program size small. This is especially important because the program code lives in ROM. Understanding the microcontroller's memory map helps target your optimization efforts. Knowing where code, initialized data, uninitialized data, heap, and stack are stored allows you to optimize each section effectively. For example, keeping constant data in read-only memory saves space in RAM. Algorithm choices matter too. Use algorithms that work in place, like in-place sorting, to avoid extra memory. Enable compiler flags that optimize for size. Use conditional compilation to include only necessary code for your application. These small changes can significantly reduce your memory footprint. Finally, testing and profiling tools are your friends. They help identify memory bottlenecks and verify that your optimizations work under real conditions. By constantly checking your code's memory use, you can make sure your embedded system runs smoothly. In the end, efficient memory use in embedded C programming isn't just about saving space. It's about making your system stable, fast, and power efficient. Whether you're designing a tiny sensor, a medical device, or a smart home gadget, optimizing for small memory is what keeps your project reliable and cost-effective.